tunneling, single and double barrier tunneling. Okay, by tunneling we mean is a particle can penetrate an energy barrier of higher value than its own energy. That we have already discussed. You remember in the quantum finite quantum well as well. Okay, we have discussed that the probability of finding, there is a finite probability of finding the particle, right, outside the well. So that is, this is basically tunneling. Okay, because even if the particle energy is less than the height of this potential barrier, still the particle might be outside the well as well, right? Now, so let me define tunneling again. So a particle can penetrate an energy barrier of higher value than its own energy. Okay, here you see the energy barrier is much higher than the particle energy E, still it's managed to penetrate. So this is known as basically tunneling. Okay, now this tunneling phenomena, this is a quantum mechanical phenomena obviously, and this is not possible according to classical concept. Now there are several applications of tunneling phenomena. For example, if we get time, we will discuss scanning tunneling microscope, we will discuss scanning electron microscope. In these you will see that there is quantum mechanical tunneling. In other words, the electrons will come out even if the barrier height is more than the height of the, or more than the energy of the electron. Okay, also we have learned hot electron effect, right? Hot electron effect in our when we were discussing short channel effect. And the hot electron effect as well, the electron energy is not more than the band gap of the SiO2 layer, you see. So SiO2 has band gap around 8 electron volt, right? But the electrons in the channel will not have that much amount of energy, but still it will sometime it might manage to cross SiO2 layer and can reach to the gate polysilicon layer or gate metal layer, right? So that is again a quantum mechanical or a tunneling phenomena. Now what we are going to do now, we are going to study that if instead of well, if I have a barrier, okay, so I have a barrier of height say V naught, right? I have a barrier of height V naught, and x equal to, say, this barrier width is A, okay, and the electron having energy E which is less than that of V naught. Okay, electron having energy E, say there are three regions, region 1, region 2 and region 3. Okay, and the barrier is exists between in region 2, right, of height V naught. Now the thing is, there might be different situations. For example, one situation is that E greater than V naught. Okay, if AE is greater than V naught, that is the energy of the particle is greater than that of V naught, then it is 100% certain that the particle will be able to cross the barrier. Okay, this is classical case, right? constant. If this energy is more than that of the height of this barrier, then it is 100% certain that the particle will be able to cross the barrier, right? But quantum mechanically, there is a possibility that particle might reflect back. Okay. Quantum mechanically, it is possible that even if the energy of the particle more than that of the barrier height, still the particle will be able to reflect back from here. If the energy of the particle is more than that of V naught, still it might be able to reflect back. Okay. There might be another situation where the energy of the particle is less than that of the barrier height. Okay. Classically, it is 100% certain that here will be able to cross, here it will not be able to cross. Okay. Again, this is the classical concept. Quantum mechanically, the particle might cross this barrier even if the energy is less than V naught. Okay. So this is, so it can penetrate the barrier. Okay, quantum mechanical wise. So it can cross the barrier. Now, again, we can use Schrodinger equations, okay, and find out these situations, okay, when it is crossing the barrier, when it doesn't cross the barrier, and so on and so forth. So you already know the Schrodinger equation, so let me write it once more. This is the Schrodinger equation, right? Where V is the potential energy that we know. We used to use U, but it's up to you. You can use V because I have named as V naught the energy barrier, so I have written V. So this Vx is function of, this is function of x, right? Because you see the way we have drawn this, you see here at x equal, I mean the width is a of this barrier. Okay, so V is varying with x, but fortunately it is like it is 0 here and it is 0 here, and its value is V naught between x equal to 0 and x equal to a. Okay, so that will make our life easier. Otherwise it would have been very difficult to solve the Schrodinger equation, okay, the way we used to solve it. Okay, now again we can find out, we can have like write Schrodinger equation at three different region: region 1, region 2 and region 3. Okay, so in region 1 V is equal to 0, so this let's write it as 1. Okay, sorry, my pen is not, okay, right? So we can write psi 1 x is equal to a to the power I k1 x plus b to the power minus I k1 x. You remember, where k1 is equal to 2me by h line square, right? Similarly, in case of region 2, here uh, v is v naught, okay, this is not equal to 0. So here of course k2 can be written in the similar, so this is k1 square, okay, sorry about that. So k2 square will be equal to this, okay, right? 2me minus v naught over h line square. H line is the reduced Planck constant, that is h over 2 pi, and this is k2 square. Similarly, this one is k1 square. And also in region 3, psi 3x will be, say, again here k3 square will be equal to 2me over h line square, which is nothing but k1 square, right? Now you see here, since there is no potential disturbance at region 3, so you see in the region 3 there is no potential disturbance, right? So there is no way that this particle wave function associated with the particle will decay in region 3, right? If that is the case, we can consider this should be equal to 0. This g term should be equal to 0, since there is no potential disturbance at region 3, so that it can't to reflect the wave after it reaches the region 3. Okay, so we can assume that g is equal to 0. So now we have like three equations, psi 1, psi 2 and psi 3, and also we know that we can use some boundary conditions. What will be the boundary condition? Boundary condition will be psi 1 x equal to 0 is equal to, sorry, equal to psi 2 x is equal to 0, and psi 1 dash x is equal to 0 is equal to psi 2 dash x equal to 0. Okay. Similarly, we can have boundary condition in x equal to a. Here psi 2 should be equal to psi 3, and psi 2 dash should be equal to psi 3 dash. Okay, because we know that in case of Schrodinger equation, the wave function and first derivative are continuous, right? Because the Schrodinger equation contains second order derivative, so the psi and first derivative should be continuous, otherwise the second order term will diverge, you remember? So that is what we are basically writing as a boundary condition. So wave function is continuous at x equal to 0. So where is x equal to 0? This is my x equal to 0. Okay, so wave function is continuous at this wall, and also the first derivative is continuous at this wall. Okay, that is what I have written in these two equations. Similarly, wave function is continuous in at x equal to a, and also it is first derivative is continuous at x equal to a, right? So I'm just keeping a lot of steps. All I wanted to show you the conditions uh, for penetration of the barrier, even if the energy is uh, less than that of the potential barrier. So all what I want is to show these two conditions in case of quantum world. Okay, this is my goal, that to show these conditions for the quantum world, so I can show you that the particle might tunnel even if even if the energy is less than the potential barrier, or particle might reflect back even if the energy is more than that of the potential barrier, right? So this is what I will try to show you. So I'm just skipping some of the steps, okay? And using these boundary conditions, it is possible to show that B over A, what is B? You remember B, A and B is the coefficients in the solution of psi 1 x, okay? B over A is can be written as k1 square minus k2 square 1 minus e to the power I 2a k2. Sorry, are we recording this video? I forgot to switch it on. Is it being recorded?
Yes, sir.
Okay, thank you very much. Thank you. So k1 square plus k2 square whole square minus k1 square k1 minus k2. Sorry, it is my mistake. Give me a second. How to do that here? So, this will be B over A, okay, and similarly it is possible to find out F over A. Okay, so B over A is this, and F over A is this. Now, the way we define tunneling probability and reflection probability is this, okay? We define tunneling probability T as mod of this F over A square, okay? Because you see here, and psi 3 contains F term, okay? Psi 3 contains F term, F e to the power I k3x, okay? So F over A will give you the factor associated with tunneling probability, whereas B over A, B is uh, e to B is associated with e to the power minus I k1x, okay? So B over A will give you the term associated with reflection probability from this wall, okay? So B over A will give you the term associated with reflection probability, whereas F over A will give you the probability of the particle to reach in the region free, okay, from region 1. Now, so the way we define tunneling probability T, okay, tunneling probability T similarly reflection probability okay. So we can plot T versus E over V naught. Okay. What is E? You remember E is the energy of the particle or energy of the electron. Okay. And V naught is the height of the potential barrier. Now, I already mentioned in case of classical approach, if the energy E is less than V naught, the particle will not be able to penetrate the barrier. So if I write say 1, 2, 3, 4, 5, so on, okay. So if below E over V naught is below 1, then particle will not be able to cross the barrier in case of classical approach, right? But in quantum mechanics, you see that there is a finite possibility for the particle even if to reach or to penetrate the barrier, even if the energy will be less than that of the barrier height. Okay, so if I plot this tunneling probability, then it is possible to show we will have curve of something like this. Okay, and even in the even energy of the barrier is even electron energy is more than that of the potential barrier, it is possible that the particle might reflect back. So the transmission probability T will not be equal to 1. That is also possible to show if you plot this expression. Okay. Now the thing is, there is series of transmission resonance. By transmission resonance I mean where the T will be equal to 1. Okay, so there are series of situations where T will be equal to 1. Okay, now we can find find the positions where T will be, or conditions where there is 100% certain that the particle will be able to cross the barrier. Okay, so we can we can simplify the above expression in this form. And here you see that full transmission will occur when full transmission means t equal to 1, right? Will occur when sin k2a equal to 0. Okay, sin k2a equal to 0. That means k2a equal to n pi, where n can be of various values 0, 1, 2, 3, 4 and so on. Okay, now we know that these are k is the k2 is nothing but 2 pi over lambda, right? K is nothing but 2 pi over lambda. What is lambda? Lambda is the wavelength in region 2, right? So we can, from these two, we can find out A is equal to n lambda 2 over 2. That means, so the complete transmission will occur when the barrier thickness is an integral number of half of the wavelengths. Okay, barrier thickness, what is barrier thickness? Barrier thickness is A, right? So the complete transmission will occur when the barrier thickness is an integral number of half of the wavelengths, and this situation is known as transmission resonance. This situation is known as transmission resonance. Okay, transmission resonance. Now let's elaborate it little bit more. So whatever we have discussed so far is the case when E is more than V naught. You see, E is more than V naught. Now, if E is less than V naught, okay, if E is less than V naught, and also we assume A is sufficiently large, A is the thickness of the barrier, then how this equation will simplify? Okay, what will be the form of this equation? What equation we are talking about? We are talking about T, okay, that is the tunneling probability, right? So how this equation will change when E is less than V naught and we are considering A sufficiently large. Okay, so again this can be visualized if we simplify this sin k2a. Okay, so what is k2? You remember k2 is 2m e over e minus v naught over h line square whole root, because it is k2, otherwise k2 square is this term, right? So this you should write in this fashion, because here we are assuming that E is less than V naught, right? E is less than V naught, and this can be written as I shine hyperbolic. I'm sorry, there are two H's, so I'm writing this as hyperbolic H like this. Okay, so now if A is very large, okay, if we assume that A tends to infinity, then it is possible to show this as I over 2 exponential Okay, it is possible to show that this sine hyperbolic term like this. Okay, this is you can also write as e to the power say alpha a. What is alpha? Alpha is root over 2m v naught minus e h line square. Sorry, it should be square. H line is square. Okay. Now so alpha will be 2m v naught minus e h line square, and of course that should be greater than 0, right? Because v naught minus e is the positive term, right? So then it is possible to show t is equal to 16e. Sorry, I'm just keeping uh, lot of steps. It is possible to show then that transmission probability will be equal to 16e v naught minus e over v naught square e to the power minus 2 alpha a. In other words, it is basically exponentially decaying. This tunneling probability is exponentially decaying, okay, as a function of width of the barrier, as a function of width of the barrier. Okay, so let me draw what I mean by that. So if the if this is the say wave associated with the particle, then this will basically exponentially decay. It will decay inside the barrier, and then again, so this is our region 1, this is our region 2, this is our region 3. In fact, I have some number, okay, just to show you. Say V naught equal to 0.2 electron volt, okay, and I am assuming E is equal to say electron volt, say 0.01 electron volt, 0.1 electron volt, 0.2 electron volt. All I am trying to do is to show you for different values of E and V naught. If I put this in this expression T, what should be the how those values look like? Okay, for A equal to 1 nanometer, it will be around 8.86 10 to the power minus 3. Okay, for A equal to 2 nanometer, it is obviously even lower. Okay, as you see energy of the particle increases, the tunneling probability will obviously increase. Okay, right? So with energy of the particle increases, the tunneling probability will increase, and with thickness of the potential barrier, the tunneling probability will obviously decrease, right? Now the thing is, so this is a single barrier case. This is a single barrier case. We might have multiple barriers. We might have multiple barriers. Okay, so we will discuss uh, double barrier case now. Okay, so we have discussed single barrier case. We will now discuss double barrier case. Okay, in case of double barrier, the reason we want to discuss double barrier case, because we have a device known as RTD. Okay, we have a device, practical device actually, which is resonant tunnel diode. Resonant tunnel diode. Okay, that device have a structure which has two barriers separated by a potential well. Okay, so I thought that we should discuss, uh, so that you understand RTD, we should discuss double barrier case. Okay, that will makes our life easier. Now, so an interesting situation will occur when we will have two barriers and separated by a potential well. So we have two barriers separated by a potential well. So how the structure will look like? The structure will look like this. So you see there are 5 regions now. What happened? Sorry about this. Not sure what happened. So you see there are 5 regions. Region 1, region 2, region 3, region 4 and region 5. Okay. Say 0, x equal to 0, a, say this is a plus l, 2a plus l and so on. So the barrier width is a and well width is l, right? So this is our a and this is our l, right? So this is the direction of x. Here v is equal to 0. This is v naught, v naught, v equal to 0. Here also v equal to 0, right? And the particle having energy E, right? So this is similar to that of our earlier example. The only difference here is we have two barriers and the barriers are separated by a potential well of with L, right? So here also we can apply Schrodinger equation and write the equations for different regions 1, 2, 3, 4, region 1, region 2, 3, 4, 5. Okay, and we can similarly write consider boundary conditions considering both psi and psi dash continuous at different boundaries. Okay, psi and psi dash continuous at different boundaries. So it is possible to show, okay, again I am not very keen to discuss the entire steps to reach this particular solution. All I am interested in to show you the situations or cases which will lead to uh, tunneling. Okay, so it is possible to show that the tunneling probability T can be written in this fashion. If you use Schrodinger equation is five different regions and use this psi and psi dash continuous for at these different boundaries, it is possible to show that T transmission probability, you remember the way we define transmission probability is the coefficients in region 5 over the coefficients in region 1 mod of square of that is basically the transmission probability in this particular case, right? Now where R1 and T1 are the transmission coefficients and the reflection coefficients, R1 reflection coefficient and this is transmission coefficients of a single barrier, right? And along with this, it is also possible to show that theta, in fact tan theta is this, where of course we know what is k1 square, okay, and what is k2 square, right? Now for t equal to 1, so t equal to 1 will happen, okay, when this sine k1 L minus theta equal to 0. So t equal to 1 will be when sine k1 L minus theta equal to 0, right? So you see k1 L minus theta, that means equal to n pi, okay, so and so on, right? So this will happen, that is the transmission probability, or the particle will certainly able to reach region 5, okay, will be able to reach region 5, because the transmission probability we are considering between region 5 and region 1, okay, when sine k1 L minus theta equal to 0, okay, or k1 L minus theta is equal to n pi. Now in this particular case we can uh, take our discussion a little bit further by assuming a simple extreme case, okay. What is that? Let's assume that V naught much greater than E, okay. What I am saying, then we can use this relation, okay, and take our discussion bit further for a simple case when energy of the particle is much less than the barrier height. This might be the case, right, that energy of the barrier is much higher than that of the energy of the particle, okay. In that case, if you look here, in that case, okay, you see k1 square will be less and k2 square, okay, will be large, right? Now if you consider that situation, then tan theta will be tends to 0, right? Tan theta will be tends to 0, okay. Now if tan theta tends to 0, that means theta tends to 0. In other words, then k1L will be equal to n pi, okay. We can write 2me by h line square whole to the power half equal to n pi over L, right? So what is E? E then will be equal to h line square by 2m n pi over L square, okay. And if you remember our discussion before mid-sem, we have found out similar expression for the energy in a potential well. You remember, in a potential well we have said energy levels which has values, okay, and we designate that as En, okay, discrete quantized energy levels, which is h square over 2m n pi over L square, okay, and we designate that as En. In other words, this is exactly the same result for the quantized energy levels in a one-dimensional quantum well. So we can say that in this double barrier case, T will be equal to 1 when this energy is same as that of the energy level here. Okay, that is what we have seen, right? We are discussing T equal to 1 case, and we have found out that when V naught is much greater than E, in that particular example, we saw that energy of the particle is nothing but the same energy level inside the potential well. Okay. So what does that mean? This means that if incident electron energy E is same as that of the different one of the energy level of the quantum well, then the transmission will be very high. Okay. Or we can also say in this fashion, if the incident electron energy is different from these quantum well energies, then the transmission probability will be low. Okay. So people developed RTD, resonant tunnel diode, okay, by using aluminum gallium arsenide and gallium arsenide. So people have developed RTD, resonant tunnel diode, using, so this is our, you remember, so this is our, say, aluminum arsenide, say this is my gallium arsenide, again this is gallium arsenide, aluminum arsenide, and so on. You remember gallium arsenide has a lower band gap and aluminum arsenide has a higher band gap. So this is my EC, this is my EV. Okay, so they put layers of very thin aluminum arsenide, then gallium arsenide, then again aluminum arsenide, gallium arsenide, and so on. And if this quantum well, so this is my quantum well, if this quantum well is thin enough, then what will happen? So this is my barrier, sorry. So this is my well and this is my barrier. Okay, so I will have E1, E2, E3 and so on in this well, right? And I have electron which is have energy E. Now I can plot T. Okay, T increases in this direction. Okay, so T is maximum here, 1, and this is the energy. So say this is my E1, this is my E2, this is my E3 and so on. Okay, say this is 1, this is 10 to the power minus 2, 10 to the power minus 4, 10 to the power minus 6, 10 to the power minus 8 and so on. Okay, so you see when energy is less than that of E1, energy of the particle is less than that of E1, the probability of tunneling is very less. Okay, but as you keep on increasing the energy of the particle and it comes at the level of E1, the probability is maximum, that is say 1. Probability is maximum here, you see 1. Then again when the energy will be between E1 and E2, the probability will again decrease. But then again it will increasing at when the energy of the particle is exactly same as E2, then the transmission probability is maximum, that is 1. Okay. Similarly again this will happen. So this is how you see the transmission probability will be maximum when the energy of the particle is in line or aligned with one of the levels in the quantum wave. Okay. Now this is a simulated plot. Okay. In actual device, people plotted I over V, that is current over voltage. Okay. And they found that the current increases after certain voltage. Sorry. The current increases after certain voltage, current decreases. Okay. Then again it increases, then again it decreases, then again it increases, right? So this is a negative resistance case, you see, where even if you are increasing the voltage, the current is decreasing. So this is a negative resistance, example of negative resistance. Anyway, so this is a RTD plot of current versus voltage or current versus energy, where you see the current is decreasing. Why the current is decreasing? Because the probability of tunneling decreases when you are coming between E1 and E2. But when you are aligning with E1, the current is large. Again you align with E2, the current is again large. But in between E1 and E2, the current starts decreasing. Okay. Right. So let me repeat it once more. So as E increases, tunneling will increase, reaches a peak at E equal to E1. After that, further increase in E will result in decreasing in the current. And you will see negative resistance and all that. So this is an example of quantum device, that is resonant tunnel diode, where we have two barriers separated by a well, and these two barriers dimension and well dimension, if they are reasonable enough, you will be able to see such functions from the device. Okay. So we will stop the quantum mechanical discussion here. We will get back to this discussion again later on when we will discuss for example those ACM, STM and so on, where those are characterization equipment, scanning, tunneling, um, and scanning electron microscope, scanning tunneling microscope, those characterization equipment, and we will see that there the electrons will basically coming out by penetrating the barrier, even if the barrier height is larger than the electron energy. Okay. There we will use this similar concept to discuss the characterization equipment, right? So here we will stop this, our quantum mechanics discussion. The next thing we will start is basically nano fabrication. So nano fabrication we will basically start in the next class tomorrow. In the nano fabrication we will start with uh, the conventional photo lithography. Okay. Again, these things we will discuss in a very very briefly, because I am assuming that photolithography is known to you. Okay, so we'll discuss very briefly. We'll give you the concept of photolithography. We'll discuss e-beam lithography. Okay, e-beam lithography will cover with reasonable detail, right? Photolithography, where we use UV light to expose uh, expose the substrate, okay, and achieve structures in the micro domain and even in hundreds of nanometer domain. But if you want to go very tiny nanometric level structure, one should go for e-beam lithography. But in e-beam lithography is much slower compared to photolithography. So e-beam lithography is not ideal for batch fabrication. So you can't have in e-beam lithography, you can't have like thousands of devices in one go. Okay, it is very slow. Whereas in photolithography, you can have large number of devices in one go. Okay, so we will go through photolithography, e-beam lithography, okay, like positive resist, negative resist, and so on. If time permits, we will go through bit of etching, sputtering, etc. Okay, and then we might move and discuss bit of double pattern lithography. Okay, where we will see that how one can increase the resolution of the lithography system, okay, and develop devices which is much smaller compared to what can be achieved through conventional photolithography approach. Okay, so I am stopping here today. Now I would like to know from you, um, how was your exam? Was it okay?
Yes, sir.
Uh, Sir, this is Balakrishna. Sir, the exam was okay, sir. There was but a little problem in MS Teams. I was unable to upload the documents even before the time.
Right,
And at that time, I got a mail from the MS Teams also that some unauthorized login has been gone on and my account has been blocked. That is why I have sent you a mail. I have tried
right,
to upload it in the inbox also, but it was not happening that time also.
right,
This
right,
is Arjit sir. I also faced the same problem while uploading because of a large file size, I think.
right.
Yes, sir. This is Dinesh, sir. I have also same problem
So I have
regarding
uploaded in the chat
at that
box
time.
of team.
Right, right. Yeah, some of you did send me email attaching your copies. Right. Um, okay, I don't know. I will try to give you probably a little bit more time if possible. Um, but yeah, please do try to upload it in MS Team itself rather than emailing me, because that floods my mailbox. Right. So is there anyone who missed the test? I mean, I didn't, I have dumped all the files, but I didn't check whether anyone is missing or not. So is there anyone today who missed the test? Okay, right, right. Okay, anything else you want to say about the test? Was the question was okay or it was difficult? Uh,
It was okay, sir.
right. So there were altogether three sets of questions. Probably you know because probably you have talked to each other after the test. So there are three sets of questions. I try to maintain similar standard in all three sets. Mm, so I will let you know once I check the answer papers. I haven't started checking them. Okay. So I will um, keep on covering the syllabus, and there will be, I don't know, there will be one more test or two more tests depending on the time I have. I will see, and again I will let you know at least 1 week before that when the test will be. But keep on, please go through, please maintain your pace, and keep on studying things as I am covering. Okay, please don't leave it for later. So I will upload this tunneling part today, okay, in the MS Team. Please go through this. I think this RTD thing is there in the conventional Z's book, Semiconductor Devices or Semiconductor Physics by SMZ. But if you don't have that, I can photocopy and upload that part as well. But I need to check from where I covered that tunneling part. It was an old note, so I need to see the which book it was. Okay. So tomorrow we will try to cover a bit of nanofabrication, as I just said, lithography, etching, and all this. Uh, and we will finish nanofabrication probably in coming Monday next week. Okay. Okay. So thank you very much.
Thank you, sir.
Thank you, sir.